So earlier when we were developing energy conservation, we realized that when you had forces like friction, dissipated forces, that some energy would be transformed into internal energy associated with the random motions of the molecules in the objects involved. We called that thermal energy, and we kind of just left that there at the time. Now we're going to loop back to that, and the goal will be to connect this thermal energy with temperature. So I'll take a quasi-historic approach to this over the next couple of videos. And I'll start by giving an initial definition, which I'll just define it operationally and say that temperature is that thing measured by a thermometer. When we take that definition, we'll use that to start to think about setting up temperature scales, and then eventually we will connect it all to thermal energy. Okay, so I've mentioned temperature scales, so it might be just worthwhile to ask yourself again, what is the point of having a temperature scale? Why do we quote temperatures, say, in Celsius or Fahrenheit or Roncanes or whatever other unit that you might like? And hopefully we're agreed on that. That's to facilitate communication. You need to know that, if the weather report says it's 30 degrees outside, you need to know, that's probably going to be a pretty warm day. Unless, of course, you live in only one of a couple of countries where you would look outside and say, that's going to be a pretty cold day. But either way, in a certain sense, it doesn't matter. As long as everyone agrees on what it is, that's about all we need. So it's just to communicate the temperature so that people can say, okay, this is how I'm going to dress today, or whatever they need. So how can we set up a common temperature scale? Well, one way you could do it is you can say, all right, here is my temperature scale, and what I need are a couple of temperatures that I can replicate pretty easily, that I can use to calibrate things. So for instance, we could go and stick a thermometer into an ice water bath, wait a while for the level to stabilize, and then name that whatever we want. For instance, we could name that 0 if we are doing the Celsius temperature scale. Alrighty. And similarly, so ice and liquid water coexist here. We'll call that the ice point. And similarly, we can look at, say, the boiling point of water would be a good example, where the gas and the liquid phases coexist. And you could give that a name, maybe, let's say 100 if we're doing the Celsius scale. Now, to be clear, there is absolutely no reason why you need to use the boiling point and the ice point of water. Any two agreed upon reference points will do, and we'll see that other scales will make other choices. For instance, you could look at the Fahrenheit scale. In the Fahrenheit scale, 0 was the lowest temperature Fahrenheit ever measured in the part of the world that he lived in. So he called that 0. And 100 is the temperature of the blood of a freshly slaughtered chicken. So he called that 100. Now you can see that there are some reproducibility issues with those. It makes it very hard to calibrate something in the original conception of the Fahrenheit scale. Waiting around until the coldest day he ever recorded rolled right back around again. You know, he might be waiting a while for that. And similarly with the chicken, you know, what if the chicken's sick, right? If it's got a fever, that's going to throw everything off. And, you know, let alone having to worry about, you know, how fast do you drain the blood. There's just a lot of technical issues with that. Grossness and slaughter of critters notwithstanding. Well, fortunately, people who are fans of his scale realized that in the original conception of his scale, water froze at almost exactly 32, and water boiled at almost exactly 212. So they said, you know what, let's redefine the system so that so the ice point is 32 exactly, and the boiling point is 212 exactly, so that we have access to more reproducible choices. But there's nothing particularly special about using the freezing and boiling point of water other than it's readily accessible in labs. Now, should you find yourself needing to convert between readings on the scale, one thing that you have to be careful about here is that when you have a temperature reading, at least the old school way of doing things is you put the degree sign in front of the C or the F. So if the degree sign is in front, that means that that is the actual reading that you are reading off the thermometer. On the other hand, if we take a temperature difference, so for instance here, the difference in, maybe it's be better to use a different color here. So for instance here, the difference in temperature between these two will be 100 C degrees. Likewise here, the difference in temperature between these is, 180 F degrees. So if it's a reading, the degree sign goes in front. If it's a difference, the degree sign goes in back of the letter. Don't worry, when we get to kelvins, it'll be even more confusing. So when you're converting temperatures, it matters whether you're converting a difference or a reading. So if you're converting differences, we can take a look and say, well, between these two known temperatures, this is a difference of 100 C degrees, and this is a difference of 180 F degrees. So that's going to be a ratio of 9 to 5. So if we need to convert a temperature difference in Celsius to a difference in Fahrenheit, all we need to do is multiply that difference by 9/5 to account for the size of the degree, for the fact that there are more Fahrenheit degrees in a temperature range than there are Celsius degrees. Or you can flip it around, and if you have a difference in Fahrenheit, you would multiply by 5/9 to account for the difference in the size of the degree. So that's if you're converting differences. Now, what if you're converting readings? Here we've got to be more careful. Here, when we're converting readings, the issue is that there is there is a common temperature, but it's not a very polite one. But the problem is we don't have 0 lined up. 0 Fahrenheit is substantially colder than 0 Celsius. So when you convert temperatures, it's going to be a two-step process. If you're going from Celsius to Fahrenheit, let's say, the first thing you're going to do is take whatever your reading is, let's say it's 50 degrees C, you're going to be interested in finding out how many Fahrenheit degrees there is. So if this is 50 degrees C, the difference from 0 to 50 is 50 C degrees. You would multiply that by 9/5 to get that there are going to be 90 Fahrenheit degrees above the ice point. But then you're going to have to add 32 to get 122 degrees Fahrenheit in order to account for the fact that the ice point in the Fahrenheit system is not at 32. So recapping, you'll take your Celsius temperature, multiply that by 9/5, and what you're really doing is you're taking the difference off of 0, but usually we don't bother writing the -0. But really that's what you're doing. So that's adjusting for the size of the degree. And then you'll have to add 32 to account for the fact that Fahrenheit calls the ice point 32 rather than 0. Now, if you do the process in the other direction, you would take whatever your Fahrenheit temperature is, subtract it off of 32 to get the temperature difference off of the ice point. You would multiply that by 5/9 to correct for the size of the degree, and then you would add 0 because the temperature of the ice point in the Celsius system is 0. So that will give you that the Celsius temperature will be 5/9 of the Fahrenheit temperature minus 32, and then I'll erase this right away. You would add 0 to correct for the reference point that you're using. So if you're converting readings, all you got to do is either multiply by 9/5 or 5/9, depending which way you're going. If you're converting differences, you multiply by 9/5 or 5/9, depending which way you're going. If you're converting readings, you have to both change the size of the degree and handle the offset for the fact that the Fahrenheit system makes 32 freezing instead of 0. So let's just do a couple of examples of that real quick to maybe help clarify that a bit. So let's start by taking 45 F degrees and converting that to C degrees. Now the first thing you need to ask yourself is this a difference or a reading? Well, since the degree signs are after the capital letter, that's a difference. So we will use that the delta TC is 5/9 delta TF. So this will be 5/9 of 45 F degrees will give me 25 C degrees. Alrighty. Now let's go and do 45 degrees Fahrenheit to degrees C. So here, the difference now is the degree sign is in front of the F. So this means we're converting readings. So we'll have to say that the temperature in Celsius is 5/9 of the temperature in Fahrenheit minus 32. So it'll be 5/9 of 45 degrees minus 32. That's going to yield us 7.22 degrees C. And maybe one more example that would be of interest is to ask yourself, is there a temperature on the scale, is there a number on both scales where the temperature is the same? You know, is there a particular number that in either scale it would be the same temperature? Turns out the answer is yes. So let's figure that one out. So here we want to find the temperature such that it's the same in both Fahrenheit and Celsius. So we can just make both TF and TC equal to T. That'd be 5/9 5t minus 32. So, okay, we can multiply everything through by 9. T equals 5t minus 32 times 9. Let's see, that's 282, right? And then, oops, sorry, 5 times 32. So that's 160. Okay, subtract 5t from both sides. 4t equals negative 160. So it turns out that at negative 40, it doesn't matter if it's Fahrenheit or Celsius, it's the same temperature reading. So at exactly negative 40 degrees C, that is also negative 40 degrees F. Darn cold either way. But if you don't like this particular way of doing the temperature conversions, this does give us an alternate way to do it. Instead of calculating differences off of 0, we could calculate the differences off of negative 40. So let's think about how that would work. So let's say I'm going from Fahrenheit to Celsius. So the first thing I can do is I can take my Fahrenheit temperature and I can subtract a negative 40 from it. That will give me the difference in Fahrenheit degrees between the temperature reading you care about and negative 40. So the next thing you can do is convert for the size of the degree, 5/9, and then you'll add to that the same the reference point, which also just happens to be negative 40 degrees C. So if I clean up the algebra just a little bit, I can write that the temperature in Celsius will be 5/9 of the Fahrenheit temperature plus 40 minus 40. And if you do this again, going the other way around, it's exactly the same logic, except instead of 5/9, you have 9/5. So the Fahrenheit temperature going, if you need to go from Celsius to Fahrenheit, you can say it's 9/5 of the Celsius temperature plus 40 minus 40. So maybe that's an easier way to remember it. Take whatever temperature it is you need to convert, add 40 to it. Then if you're going to Celsius, multiply by 5/9. If you're going to Fahrenheit, multiply by 9/5. And then subtract 40. That's also a perfectly good way to do it. A lot of people, by the way, will also construct a similar one between 50 degrees Fahrenheit and 10 degrees C, but I'll leave that as an exercise for the viewer. All right. So the problem with traditional thermometers is pretty much eventually things freeze. And so what if you want to go to lower temperatures? Well, it turns out that we could use what's called a constant volume gas thermometer. So the way it works is, let's say here's the sample of gas whose temperature I want to know. I'll just go and hook this thing up to a manometer, except the manometer will have a special little difference to it. Sorry, a barometer. I'm going to hook this up to a barometer. My bad. All right, now the difference is that you can remove or add liquid here. This is a volume adjustment reservoir. So you can let your gas come to equilibrium at whatever temperature you like. Then what you do is you adjust, you either add or remove liquid here until the liquid over here always sits at this reference level right here. This ensures that the volume doesn't change as the gas expands or contracts as it gets warmer or colder. Because what you do is you just add or remove liquid to get back to this reference level. And then it goes the same from there. You use this column height right here. This is going to be evacuated, so the pressure is roughly 0 right there. So it's going to measure the pressure. But it turns out that the pressure, if the volume doesn't change, the pressure is directly proportional to the temperature, at least as long as the gas is of adequately low density. And an amazing thing happens. If you plot the pressure of the gas against temperature for different gases, what you'll find is that, first off, it pretty much doesn't matter what the gas is, but it does matter what its density is. So basically, it's mostly for different densities of gas. Now, at some point as you're going along, depending on what the gas is made of, what the density is, etc., your gas is going to, something like that. Yeah, your gas is going to go liquid. But if you interpolate everything out, liquid or solid, if you interpolate everything out and you can get lower and lower temperatures, the less and less dense the gas gets. You find that all of these pressure versus temperature curves that you get for different choices of gas, they all hit a pressure of 0 at exactly the same temperature. And that temperature is negative 273.15 degrees C. So we call this temperature absolute 0. And why do we do that? Well, the thing is that once the pressure hits 0, it doesn't make sense to talk about a negative pressure. Bleeding edge cosmology about dark energy notwithstanding. It doesn't make sense to talk about a negative pressure. So the pressure of 0 is as low as you can go. And since for every gas they all hit that same lowest pressure at the same point, that means that that temperature is as low as you can go too. So what this does is this gives rise to what are called absolute temperature scales. Oops, sorry about that. So since there's a lowest possible temperature, an absolute temperature scale, what you do is you just decide that that lowest possible temperature is 0. So one such scale is the Kelvin scale. And annoyingly with Kelvin, there is no degree sign before or after. There used to be back in the day, but then the people who got all official about it decided that it was always clear from context whether you were talking about a reading or a difference. And so you are expected to keep track of that. So there is no degree sign in the Kelvin scale. But there's still a degree sign in the Celsius scale. And so what the deal is that a temperature of negative 273.15 degrees C, which is our lowest possible temperature, absolute 0, we say that that is 0 Kelvin. And then conceptually, we can just make the upper point here the freezing point of water, which isn't quite right. I'll correct myself twice on that. And the whole trick with Kelvin is that the degrees are the same size. So the temperature difference between absolute zero and the freezing point is 273. So since the degrees are the same size, if you're converting differences, a difference in Kelvin is a difference in Celsius. So all you have to do is change your C degree to a K and you're done. Now if you're doing a reading, since the degrees are the same size, you don't have to adjust for the degrees, size of the degrees. You just have to shift all the readings by 273.15 to account for where 0 is on the Kelvin scale. This isn't the only temperature scale that does that. Engineers will often use the Rankine scale, which is sort of the Fahrenheit equivalent. 0 Rankine is absolute 0, and then it's the same deal. You just add a bigger number to the Fahrenheit temperature to get the Rankine temperature, but it's the same idea. Not that we'll be using that, but just to throw it out there that this isn't the only one. All right. Now, those of you who may be assiduous readers of footnotes in textbooks may be already ready to call me out that the upper reference point is not the freezing point of water, and you are correct. Until recently, with the redefinition of SI, the upper point was actually the triple point of water. It turns out that at the rather low temperature of 611.73 pascals, if you are at 273.16 Kelvin, the gas, liquid, and solid phases of water will simultaneously exist. So there are companies that make sealed glass vessels such that if you go through 273.16, the pressure of the vessel will be 611.73 pascals, and you can plain as day see the three phases at once, and you know you hit the triple point, and that's very precise. Now, with the redefinition of SI units, the Kelvin temperature scale, and by extension Celsius, has been redefined yet again. Kelvin is the official scale, and Celsius is defined as the Kelvin temperature minus 273.15. We will get into what the new definition of the Kelvin scale is, but it's going to take us developing some gas kinetic theory to get there. So the new official status of the triple point of water is it is one of a collection of triple points of different substances that are used as practical measures for calibrating thermometers. So anyway, let's do a couple quick examples of converting temperatures here. Let's go and take 90 Kelvin and convert that to degrees C. Now here, because the degree sign is in front, that's a reading. Because that's a reading, we're going to say T Kelvin equals TC plus 273.15. So the Celsius temperature will be the Kelvin temperature minus 0.15 there. So the Celsius temperature will be the Kelvin temperature minus 273.15. So it'll be 90 minus 273.15. So there'll be negative 180. Negative 183.15 degrees C. Yeah. All right. And just for another one here, let's convert 50 C degrees to Kelvin. Well, here, since the degree sign is on the right-hand side, this is a difference. So it means that this Kelvin here is a difference. So we can just say that delta T Kelvin is equal to delta T Celsius, so it's 50 Kelvin. So yes, it is annoying that in the Kelvin measure, you just write a K without a degree sign. I find it helpful to imagine that there are still degree signs just to help keep the bookkeeping straight. Okay, so now to lead into the redefined SI definition of the Kelvin temperature scale, I need to introduce what's called the Zeroth Law. No, I'm not making that up. The Zeroth Law of thermodynamics. And why the heck is it called the Zeroth Law? I'm glad you asked. It turned out that after the first and second laws of thermodynamics had been demonstrated, people realized that you actually had to have the zeroth law of thermodynamics to make the first and second laws work. So since the dependency is that the first and second laws need the zeroth law, the clever idea is just to give it a lower law number. I really hope this is as fundamental as it ever gets and nobody finds a flaw that requires something more fundamental than the zeroth law, because I don't ever want to have to be discussing the negative first law of thermodynamics. That would be just too silly. So we'll start with a couple of definitions. One is thermal contact. Thermal contact is any sort of connection that allows a transfer of internal or of thermal or internal energy. This is usually going to be direct contact in most practical applications, but other things are possible. For instance, if you're in deep space, you could just put two objects near each other and let them very slowly radiate light at each other because of their heat. That would be a method of thermal contact. Not a very efficient one, but it would be a method of thermal contact. But usually we're envisioning direct contact here. Now I need to define thermal equilibrium. And that is a state such that if you have two things in thermal contact, there is no net exchange of thermal or internal energy. So there could be there could be exchanges. It's just that they have to be two-way streets. So if one object gives the other object a little bit of energy, the other one better be giving it right back in order for it to be in thermal equilibrium. So with all of that, we can now finally state the zeroth law, which says two systems individually in thermal equilibrium with each other. With a third system. Getting ahead of myself here. In thermal equilibrium with a third system are in thermal equilibrium with each other. All right, what does this do? What this is doing is it defines the concept, not of temperature, but just the idea of the same temperature. So, as for a practical example here, let's say I have an ice cube at 0 and some water at 0. If I put a thermometer into the water, there may possibly be some exchanges of thermal energy. But with time, the thermometer will read 0. And at that point, there's no more exchange of thermal energy between the water and the thermometer. If the thermometer, say, were too hot initially, the atoms in the thermometer on average would have been a little more energetic than the ones in the water, and so each time there was a collision between them, as we've seen before, the one with more energy loses and the one with less energy wins usually. So if we wait long enough, eventually we get to a point where, although there may still be collisions, they're just as frequent in each direction, transferring just as much energy in each direction, and then the thermometer doesn't change its reading anymore. Same thing would happen if I placed the thermometer in contact with the ice cube. So then what that means, to say they have the same temperatures, that means if I take the ice cube and I put it in the water, the ice cube's not going to melt. Any exchanges of thermal energy between the ice cube and the water will always be immediately balanced out with each other. There'll be no net exchange. So that defines the concept of having the same temperature, and that allows us to rigorously set up temperature scales. Okay, so in the next video we will start to wander our way into kinetic theory, where we will start to take the microscopic motions of atoms and link them into temperature more rigorously. Catch you in the next one.